Welcome to this lesson on special right triangles. We'll look at two of them, the 45-45-90 triangle and the 30-60-90 triangle. Let's go ahead and get started with the 45-45-90. Notice that for the 45-45-90, besides it being a right triangle, it is also an isosceles triangle. Remember, isosceles triangles are those that have two congruent sides. And keep in mind that we learned isosceles triangles have two sides that are congruent, and that's shown here by x and x. Those are called legs, and of course this would be the hypotenuse. The reason why these are important to us is because they save a whole lot of time if you're trying to find a missing angle. Now here's the good news for the SAT test takers. These special right triangles are given to you on the front page of each math section. If you're taking the ACT, you're not so lucky. You have to know these formulas because they're not given to you on that test. And so pay close attention on how you would find a missing side. Here's how it works. If you are given the length of one of the legs, let's say 4, the other leg would have to be 4 because isosceles triangles have two legs or two sides that are congruent. To find the hypotenuse, you don't even have to use any math. You simply take one of the legs and you multiply it to square root of 2, so the hypotenuse would be 4 root 2. And they're useful because, again, you see it barely takes seconds to find the missing side. So let's try another scenario on the 45-45-90. What if you're given the hypotenuse as 7 square root of 2? You can then look and discover, hey, 7 is x, which means I know the legs. The leg would be 7, and of course this other leg would also have to be 7. But of course it's not always that straightforward. Sometimes you have to deal with radicals. Good news is that we've already talked about radicals early on in this course, whereby we learned about adding them, multiplying, dividing, rationalizing, and so on and so forth. If you've forgotten, please feel free to go back and look over the radicals lesson. But let me just give you an example of what that might look like. If you're given this side as maybe 2 square root of 5, of course this other leg would also have to be 2 square root of 5. Now the hypotenuse is a little bit more interesting because it's now the leg 2 root 5 times square root of 2. Recall that you can multiply radicals. It doesn't matter if they have the same radicand or not. So this ends up being 2 radical 10. That would be the hypotenuse. One last example before moving on. What if we're given the hypotenuse as square root of 13 and we are asked to find the two missing legs? In these scenarios, just remember that if you know these ratios, you can always set up an equation. We know that the hypotenuse is always x root 2. Therefore, we can look and say, in this specific example, x root 2 has been given to us as square root of 13. Notice that if you solve for x, then you'll have the legs. So all we need to do is divide each of these by root 2 to get x by itself. Notice that these cancel out. However, since we're not allowed to have radicals as a denominator, we need to rationalize. We can't have this happen. So rationalizing simply means multiplying both the denominator and the numerator by the radical that you want to get rid of. And now the numerator becomes square root of 26 over 2, because any radical times itself is just the radicand. And this would be the end of the problem because we can't simplify this any further. Again, if you find yourself struggling a little bit with the radicals, there is a great lesson on this from this course. Just go back to the radicals lesson and just watch the videos again and attempt the problems provided. The next right triangle is the 30-60-90, which works very similarly to the 45-45-90. The only difference with this one is that the ratios are different. Notice that the hypotenuse is 2x, the short leg is x, and the long leg is x root 3. Please note that the long leg is always the one that is adjacent to the 30-degree angle every single time. So don't confuse these two. Let's try to make a little bit more sense of this. The short leg is x. And note, please, that the hypotenuse is always double what the short leg is. So x, this guy would have to be double it, which is 2x. And now the long leg is always the short leg times root 3. I always forgot what went where until one day I discovered that the 3's need to be close together. The 3's are adjacent to each other, and I use that as an anchor to help me remember what that would be, what the ratios would be on this triangle. And as I mentioned, this works in the very same way as a 45, 45, 90. So if you're given the short leg is 5, we can find the long leg by saying 5, which is the short leg, times root 3. So it becomes 5 root 3. Of course, the hypotenuse is double what the short leg is. So if that's 5, this would be 2 times 5, and that would be 10. A slightly more challenging problem might be something like this. What if you're given the long leg as 7 root 6? Once again, all we need to do is set up an equation. We know that the ratio given for the 30, 60, 90 is x root 3 for the long leg. This time for this problem, it is 7 root 6. So if we solve for x, then we'll have the short leg. And of course, when we have the short leg, we can find the long leg by doubling what the short leg is. Let's go ahead and get x by itself. So we're going to divide each side by square root of 3. And you find that root 3 and root 3 cancel out. X equals 7 root 6 over root 3. There are several ways to do this, but let me take the longer route just because it feels though you need more practice with radicals. You would say times root 3 to rationalize, since you are not allowed to have radicals as a denominator. So x equals 7 root 18 over 3, because again, any root times itself is just a radicand. However, we can't walk away from this problem just yet because square root of 18 can be simplified further. So let's take the square root of 18 off to the side and simplify it some more. Remember, when you're simplifying radicals, you're looking for two numbers, two factors that multiply to equal 18, but not just any random numbers. One of those has to be a perfect square. So how do we get 18? Well, 1 times 18. But that's not useful because neither one has a square root. Next pair is 2 times 9, and that's a great one because 9 does have a square root. So we can rewrite the square root of 18 as the square root of 2 times 9. And the advantage of doing this is that we can take out the square root of 9, which is 3. So 3 goes on the outside, and we are left with root 2. So square root of 18 simplifies to 3 root 2. And of course, because this is 3 root 2, remember there was a 7 on the outside of that, so it would be 7 times 3 root 2, which becomes 21 square root of 2 over 3. Examine the question again just to make sure that you've simplified fully. And if you look, you'll see that you're still not done with this because these whole numbers can be simplified. 3 goes into 21. 3 goes into 21 7 times. 3 goes into 3 once. So the final answer for x is 7 root 2. That means the short leg is 7 root 2. To find the hypotenuse, we just need to double the short leg. So 2 times 7 root 2 is 14 square root of 2. The final idea that I'd like to run by you as we are reviewing the special right triangles is known as the complementary angles theorem. And I'm going to start off by sketching a right triangle here. We've learned a term that we've been using all along, and that term was supplementary. And we learned that supplementary angles are angles that add up to 180 degrees. This time we now have something called complementary. Complementary angles add up to 90 degrees. So here's the fact. Anytime you have a right triangle, of course, you'll have a 90 degree right there shown by the box. Guess what? The other two angles, this one and that one, will always add up to 90. They are complementary because one of the angles is 90. The other ones have to add up to 90 because together the whole triangle has to equal 180. So there's a theorem that is centered around that fact. And it also features a little bit of trigonometry in it. And here's how it goes. So let's just say that this angle is 60 degrees. We can find this missing one because it's complementary to the 60 by subtracting it from 90. To find this angle, we would say 90 minus 60, and that would give us 30 degrees. So we know this is 30 degrees. Let's draw another pair. If we knew this angle is 80 degrees, we can find this one over here, since we know they're complementary, by saying 90 minus the 80. So this would have to be 10 degrees. These always add up to 90. Now, if we wanted to come up with an expression to represent that relationship, let's just call this first angle x. The other angle that we need is always going to be 90 minus x. And now, with that introduction, we can actually talk about the complementary angles theorem. It is as follows. The sine or cosine of one angle, let's just say the sine of angle x, which is this angle here, will always equal the cosine of its complement. So what's the complement of x? The complement of x, as we saw it, was 90 minus x. And vice versa. So if I said cosine of x, it would have to equal the sine of its complement. Well, the complement of x is always 90 minus x. These are what's known as the complementary angles theorem. Very, very important for you to know. Let's actually try an example of this. If I knew the sine of 60 degrees, what is the complement of 60 degrees? 30 degrees. So we would have to equal the cosine of 30 degrees. Let's do one more. If I knew the cosine of 20 degrees, it would have to equal the sine of its complement. The complement of 20 is 70. And we can prove this mathematically using numbers. So I'm going to use numbers for this triangle here. Let's just say this side here is 5. And let's say this side here is 12. And then let's say this side here is 13. If you wanted to find out the cosine of this angle here, remember cosine is adjacent over hypotenuse. So cosine is adjacent. What's adjacent to this angle here? Is 5. So cosine of x equals 5 over the hypotenuse, which is 13. What is the complement of angle x? The complement of angle x is this angle here. So if our theorem is true, if we do the sine of 90 minus x, we should end up with this same answer. What is the sine? Sine is opposite over adjacent. So what is opposite from this angle here, the green circled one? 5 is. And what is the hypotenuse again? Still 13. So notice the cosine of this angle is 5/13, and the sine of its complement is 5/13, as we just found out using the complementary angles theorem. So that concludes this lesson on special right triangles. Be sure you know how to use the 45-45-90, the 30-60-90, and be very well conversant with the complementary angles theorem.